evening, everyone. I would like to welcome Professor Sebastian Szybka from Jagiellonian University, from Astronomical Observatory. He is an astrophysicist. His specialty is Einstein's theory of gravity. And I'm really grateful that he agreed to talk to us today. So thank you very much, and the floor is yours.
Thank you for invitation. So good evening to everyone. I will share my screen. So thank you for invitation once more. I'm Sebastian Szybka, and I'm a cosmologist, one may say, a relativist person who works in the field of general relativity. But in fact, you may have different type of cosmologists. So cosmologists with different type of background. I'm not astronomer by training. I'm a theoretical physicist. And as you may guess, since I'm a theoretical physicist, I like equations and I work on equations. And in the case of astronomy, astrophysics, the dominant force is gravity. So as you may guess, I work on Einstein's equations because Einstein's equations are core of our best gravity theory, general relativity. And Einstein's equations there are several aspects that makes them interesting. So one aspect is that they are very old, but at the same time, they are extremely complicated. So they are older than 100 years, but they are so complicated that we still study them. So in fact, I'm some kind of a, let's say, physicist, mathematician who studied those equations. And since we cannot understand them fully, although we studied them for 100 years, one may ask the following question. So we have recent revolution, I would say, in artificial intelligence. And the question is if AI can help us with Einstein equations to understand them better. And this is the topic of my talk today. So I will talk about Einstein's equations, why they are hard to solve, what we can learn from them and what we do not understand yet, and what my expectations are related to the artificial intelligence for progress, what kind of progress I expect. But to put the things in the full context, let's move back in time to Berlin, to 1915. This picture was taken more or less at this time, I think it's 1920. You can see Einstein, I think everybody recognized him. When he was in Berlin at the time, he discovered his equations, the equations that govern gravity. And those equations exist in the same form. There was a slight change in 1917 when he added an additional constant to the structure of the equations. But from the 1917, they have all the time the same form and nothing was changed in those equations. So at the mathematical level, we have a set of equations. There are partial differential equations that come from the 1970s. And world at this time was much different when you think about our knowledge and about the technology that was at this time. So here is a postcard from 1915, I think. I mean, it's partially cut and glued, but you may see how the Berlin looked like at this time. Prussian Academy of Science was not far from this place that you can see in this postcard. You can see that there are some cars already, but there are still horses on the street. And when you think about technology, the world was much, much different. So how does the world look like at that time? I will remind you that the first commercial airplane flight was in 1914. So it was just something like very recent thing that people started to use airplanes in a commercial manner. Now, when we think about our knowledge, it was still before the discovery of proton. So we didn't, I mean, proton has a structure, but they didn't know even that the proton exists at that time, not to tell us that something about the structure of proton. Now, when you think about astronomy in 1915, So we didn't know at that time if other galaxies exist. So is there only Milky Way or are there other galaxies? We didn't know that, and there was a ongoing great so-called great debate in 1920s when they finally, after this debate, they agreed that galaxies could. Only after this debate, they agreed that the galaxies are different objects that are not in the Milky Way. So there are not just some kind of nebulas in the Milky Way, but there are like other Milky Ways, other galaxies. And the most basic thing that you can think in astronomy, I mean, you have distant stars, but we have something that you don't need special instruments to look at. We have a sun. And in 1915, when Einstein was writing down his equation, we didn't know why the sun is shining. Because you need nuclear physics to understand why the sun is shining. Because, I mean, this chemical burning is not sufficient and it doesn't agree with the models of the sun. So it's like a very, very basic thing because you cannot miss sun when you go outside. And this is relevant astronomical questions. And Einstein, when he was sitting next to his desk, imagine Einstein sitting next to his desk and writing these complicated equations, but he didn't know so many basic things. And of course, there was long time for to the first computers. There were some kind of mechanical calculators already at that time, but no true computers. We had to wait a little bit longer for them. So I show you this, I mean, just to convince you that Einstein's equations are interesting because there is like some hidden knowledge hidden in this equation. This knowledge is not something Einstein knew at that time when he was writing them down. So it's some kind of a mystery why he could discover equations that contain information that contains information about the world that Einstein didn't know about. And to give you example, so imagine we have this equation from 1915, 1917, maybe with slight modification. Recently, it may be not so recently because it's almost 10 years ago, but we had a discovery of gravitational waves. And what does it mean? It means that those equations discovered by Einstein so long time ago describe extremely tiny changes of distances between mirrors, and their mirrors move because of the gravitational waves that were created in the collision of black holes. So if you would show this to Einstein, so gravitational radiation, he suspected at that time in 1915 that something like that may exist. Okay, so he wouldn't be surprised, but he would be very surprised because he didn't believe in black holes at all. Even when at the end of his life, he still didn't believe in black holes. He even wrote a paper why the black holes shouldn't exist, in his opinion. So I hope that this evidence will tell you that the Einstein equations are interesting. And I believe, and other people, relativists, believe that there are still some secrets hidden in the structure of these equations that are relevant for our astronomical observations and for the structure of the world. So how Einstein's gravity work? So the first thing is, probably you already know that you have to forget about gravitational force. Because what Newton said that if you have two bodies, then there is a force between them and they behave because in an appropriate way because of this force. Einstein said, no, you have to look at this problem from the completely new perspective. So imagine that space and time do not exist as separate beings, but there are just one being called space-time. And this separation of time from space is artificial one. So at the physical level, you cannot really separate that. It's something that our brain recognizes that there are different things, but this is from different reasons. So this is not because of the physics. We just get used to think about time and space as something different because this simplified point of view was useful during evolution. I mean, you don't have to know about space-time when you live and when you try to survive in savannah or somewhere. Okay? So this is simplification that was introduced by our history, our evolution, but the physical reality is different. There is a space-time. And when you have energy in space-time, then the space-time is curving because of that energy that is inside. And how it's curving, this is given by the Einstein equations. You can see them here. On the left-hand side of those equations, you see geometry, and on the right-hand side, energy. They are given in terms of tensors, but probably you already know what tensors are, but I don't have to explain the details here. Just think about this way. You have geometry and energy curve space-time. Moreover, the things are more complicated. If you don't have any energy and mass are equivalent in Einstein theory. So, but if you don't have energy, then space-time still could have some degrees of freedom. So, for example, if you describe gravitational waves, you don't need any source in terms of matter filling space-time. Okay, the space-time is like some kind of a thing that can vibrate just without any interaction with additional external sources. And the question is, okay, so this is an idea and it seems to be interesting, but it's physics or just mathematics. And we have very important predictions that you can derive from these equations. Because I'm a cosmologist, so let's start with the cosmological model. So because once you have those equations and you have space-time, you can try to model different systems. So the simplest thing is just a star. Let's model a star. Then you will get, using those equations, you assume spherical symmetry and you get this shape of space-time outside of the star, or if you know the source, inside of the star as well. So you have space-time that describe star. Once you have the space-time, you can tell how test bodies, so small bodies, move in the space-time, what will happen to astronaut moving there, or planets, if you think about a gravitational field of sun, for example, or something more complicated. But you can try to describe different systems. People try to do this already in 19th century, but they were unsuccessful. So imagine that the universe, the model of the universe, is a model of a thing that is filled in a homogeneous way with matter, let's say dust. Dust is in terms what astronomers understand by dust is just, or relativist, is just matter without any pressure. So in cosmology, the particles of dust are the whole galaxies. And then those equations told Einstein that once you do that, when you construct this model, then the universe cannot be static. It has to expand or collapse. The equation that doesn't tell you if it's expanding or collapsing. You have to look at astronomical data to distinguish between these two possibilities. But once you will read out the speed of expansion and other parameters, then you will be able to predict the fate of the universe, and even you will be able to predict what was at early times, at the beginning of the universe. And of course, this was something unusual because the people believe that or the universe is eternal, or the universe was created at some point, but it doesn't change much from that time. Okay, and now we see from Einstein equation that it should be dynamic, and we have a lot of evidence. It took many years to collect this evidence, and it took like a half of a century to convince people that those early models are really models of the true universe. So we have a huge support in astronomical data. And in recent 20 years, we have like a era of the precise cosmology when the model works very well. There are some unknown things in the model, but this is a different story. It's definitely a very huge discovery. that from those equations you can learn something about real universe. Another things are black holes, and the black holes were there in 1916, I would say, because people have found, Schwarzschild have found the first solution that described black hole, but they didn't know that the solution is physical and that it describes really black hole. They assume that it describes only external gravitational field around the spherical star. And Einstein didn't believe in black holes, and it took like 60 years to convince people that those things that were hidden in those equations really exist there. And the similar stories with gravitational waves. The different thing is that originally the people, even before discovering this equation, on some different theoretical grounds, they believed that the gravitational waves should exist, but then later Einstein changed his mind, and for some time he believed that they should not exist because of some other theoretical arguments. And even like 20 years ago, not everybody was sure if they exist, but we have discovered them, and all these predictions of the theory are consistent with our observations. Okay, so to summarize this beginning part of my talk, I try to convince you that those equations are useful because we learn a lot from them about the real physical universe, not only about mathematics. It's not only interesting mathematics, but it matches to the real world, to the real universe, to the real objects that exist in this universe, like black holes. Okay. Now I will try to convince you that the equations are complicated and why they are complicated. I will tell you why they are complicated. So look at Newton's gravity. Probably you know different formula for Newton's gravity with the force between two bodies, but those equations can be written in a form more similar to Einstein equations as a partial differential equation of this type, but it fits to one line, so it's not very big. You can see it in the full form here below. So it's not extremely complicated. And people were using this equation like for 200 years, and we are still using them because in many applications that they are sufficient. Now, if you will try to write Einstein equations in a similar form, you will get a lot of terms. In a full form, there would be like 20,000 of terms. It depends how you will write them, but many thousand of terms. I will show you not everything, just 3 slides out of 1,000 because we don't have time for more. And anyway, you cannot learn a lot from that. And they are not written in a full form. The quantity we are looking at, but as you may see, I hope you may see it, they have a form of partial differential equations for the quantity called metric. There is like inverse of the metric, so they are not really in the full form, but they would be even bigger if I would put them in a full form. So they are complicated because they have many terms. Now, what kind of equations there are? You probably know different types of equations. Algebraic equations are most basic one, like this two at the top of this page. And you can solve them like the first one you can solve in exact way, just you find x as a function of k minus 2. Then you have another algebraic equation, but you cannot find, for all values of k, you cannot find exact solutions here. So you have to stick to numerical methods. Okay, you can solve them with computer, or you can use some approximate methods in general case. If k is 0, then again you can solve them, but for any k you cannot do that in general. Okay, but those are algebraic equations. Ordinary differential equations have this form like those equations here. So imagine that you are sitting in the car, you accelerate, but your acceleration, I mean, your engine has some limited power. So when the drag forces become too high, you cannot accelerate anymore. So you have a simple example where acceleration is given by this formula. So this is some kind of toy model. If you write it as a full differential equations, it's just ordinary differential equations because you have one variable. on which your functions that you are looking for that depends. And there are other types of equations, like partial differential equations, that are more complicated. And you can see the so-called Burger's equation below. Their form is not much more complicated. This equation can be used to study traffic or to study fluid flow or whatever. This nu is a viscosity parameter. It doesn't really matter. What it matters here that these ordinary differential equations are easy to solve. You can solve them exactly or using computer without any problems. If you will put 10,000 or 20 or 100,000 terms, you can still solve them with modern computers. It's not very problematic. Maybe if you want to do it very fast, then it's problematic, but in general, it's not a problem. But those equations, partial differential equations, are more complicated in terms of their behavior. So for example, they were discovered like 50 years or more ago, this Burger equation, but people still can write scientific papers on this simple equation. Okay? So because there are partial differential equations, then it becomes more complicated. And now if you will add more terms, then it will be more complicated in number of terms, but even more complicated if you try to solve them numerically, because there is no easy procedure to solve them in general case. You can get some instabilities. So all I want to say that you cannot do that in general by a brutal force that you will take a bigger computer and solve a bigger equation. It doesn't work this way because there are some instabilities and other problems. Okay. So now I hope I convince you that the Einstein equations are large and complicated and contain useful information. But there are several problems when you want to solve them. I mean, there are not many known exact solutions to Einstein equations. We have black holes, we have cosmological models, we have some approximate gravitational waves, like plane waves that are exact solutions to Einstein equations, but they are approximate in terms of the real gravitational waves that we can detect coming from space. But when you think of numerical relativity, it's not easy, it's hard. And to give you an example, LIGO is the first detector of gravitational waves. It started operations in 2002 because when people started to build it like a decade earlier, they were convinced that although we don't have relevant numerical solutions to Einstein equations that could give us prediction for the patterns of these gravitational waves, for the forms of the gravitational waves, people will find them. But the situation was strange because the observational part of this project was faster than the theoretical part. So the detector was working already. It didn't have this precision that was necessary to make a discovery, as we know nowadays. But it was working, and people were still waiting for the predictions, to have reliable predictions. Of course, there were some approximate methods that turned out to work quite well, but it was not later than in 2005 when people learned how to make numerical simulations, reliable numerical simulations of black hole collisions to find a pattern of gravitational waves coming from that collisions. And it was necessary because there was like a lot of noise in the LIGO data, so you cannot just see gravitational waves, but you have to filter noise and you have to look for some specific patterns to see if it's there or not. So those simulations were very important. And it may be that artificial intelligence, AI system, can help us in that. I put a question mark because I'm not sure. It did not help us so far, but there are some papers that you can use this artificial intelligence to solve partial differential equations in a more efficient way. So far, what I have seen, the people were solving the problems that were already solved in the traditional way with these neural operator methods, and they claim that it was faster, but no breakthrough at the moment. But it could be that in few years we will have, it would be much easier to solve Einstein's equations and learn something more about them. So the first problem was how to solve Einstein's equations numerically, and AI could help us with that. The second problem, I call it lack of information flow. There is one more specific thing when we think about Einstein equations. When you have flat space, then is one coordinate system like Cartesian coordinates, and the flat space could be always described with these coordinates. So I have space, I have points in this space, and I could give a position of the point just by setting the proper coordinate system and labeling points with some numbers. Okay? But when the space is curved or space-time is curved, in general there do not exist one coordinate system. So all these formulas for Einstein equations have to be written in a coordinate independent way. And when you have a particular solutions to Einstein equations, it turns out that they could be physically the same solutions, but they could look completely different. So in terms of what you write on the paper, you will have different functions. They would be not similar if somebody would solve Einstein equations in different coordinate system, even if the solutions are physically the same. So there are methods to test that, but it's not easy. And the most famous example is Kasner's solution, where people were looking for a solution, finding the same solution to Einstein equations many times. In 1979, 75, 75, 71, 71, 69, 68, 68, 51, 46, 21. You see? So it was like a large loss of time and energy of these people, because they discovered the same thing that Kasner in 1921. They just have written it in a completely different form, so they did not recognize that it's the same solutions to Einstein equations. And they did not recognize it because sometimes they did not look at the correct paper. There was no internet at that time, so it was harder to do that. But sometimes those solutions had completely different form and sometimes even different physical interpretation. So it was not so easy. And you have many other examples, like this Drost rediscovered the Schwarzschild solution, and then he described so-called geodesics, so how test bodies move in such space-time. But then many papers and many other people or researchers discovered what Drost discovered in 1916. So it's like a cascade of rediscovering things. It's the same thing with Einstein and Rosen. They were looking for gravitational waves, exact solution for many years, but they didn't know that Beck was discovered them in 1925. Bondi, Pirani, Robinson, and Brinkman, Taubnat, and Taub, and other things like, let's say, Birkhoff theorem. It was a very important theorem in the field of general relativity. Only recently, by recently I mean 20 years ago, maybe people learned that before famous Birkhoff, he was a famous American mathematician, Jepsen from Norway. He died as a young person and published his result in unknown journal. He discovered the same important thing, but it was just forgotten, and later somebody discovered in the library, okay, that this result was 2 years earlier than the result by Birkhoff. And the famous Hubble-Lemaitre law, and so on. And now I see a clear application of AI in this case, because if AI system could evaluate the knowledge that we have gained so far in some non-trivial way, so not like just looking for keywords, if there are similar keywords. For example, in Beck paper, there was no name gravitational wave, because he was studying those solutions in different contexts. So if they would have Google at that time, they would not found this Beck solution. Einstein would not found it. You need to have some at least artificial understanding of what Beck has written to see that it compares well what Einstein and Rosen are looking for. So, and such things are already AI system can help in this already. I don't know how to measure the influence of AI on this thing yet, but definitely this is the future, and it starts now. This was the second problem. So the first was numerics. The second problem was lack of information flow. The third problem, I call it megabit bomb. This name megabit bomb comes from Stanisław Lem, who was a Polish science fiction writer. And it simply means that too much information is just as harmful as lack of information. Because when you have too much information, even if everything is correct, sometimes there is a lot of false information, and it's harder to look for the correct one. I mean, the facts or theorem that are correct in this, but it's not just that. Imagine that you can have all these correct theorems published somewhere, but so many papers that you cannot read them. And in the field of pure general relativity, I would say, pure gravity, you have like 10 articles per day. This is on arXiv. You probably all of you know arXiv, I think. And frankly speaking, I don't have time to read 10 articles per day. I mean, there is a lot of math in these articles, so it's not just that you need like 10 minutes to read them. And when you look at the wider context, like astro PH, so the whole astrophysics, this makes already 40 articles per day. And if you want to study all articles that are in this database, it's like a 2.5 million articles. I mean, so nobody can read that and correlate if some results between different articles. I mean, human cannot do that simply. And I plot a graph. It doesn't extend to 1,000. I think it ends, say, maybe it extends to 2,000 to our year. This is a number of articles per month on arXiv, and it's growing. There is, you can see pandemic. I think here there is like a higher growth at some point, and it's a little bit steady, and then the last peak, it could be AI system that helps people to write more articles than before. Okay, but now, so my next suggestion is that the AI system can help you with looking at these articles. And already you have a system, I tried them, that can summarize articles. You can throw like 10 articles there, and they will make a short summary of all of them, and they can relate the results presented in them to your research. For example, you can ask AI system if there is something relevant for you or not. So this is helpful in this way. And there's another way in which AI can help you to solve this problem, or maybe a problem that is related to this one. But imagine that, okay, if I'm expert in general relativity, then I could read the article in general relativity that has a very short form. It's written with, I know all the definitions that appear there, and I'm used to them, and so I can read the short articles. But when there come a person outside of the field, let's say a physicist, but he is like an astrophysicist, let's say, that his expertise is not fully in general relativity, that's for him, it's harder to read this article. And now with AI, you can just rewrite the original article in a way that it's easier to understand. You can expand some definitions, not to use just this terminology, but add some explanation. So instead of 1 or 2 pages, you will have 5 or 10 pages, but you can read articles outside of your field, I would say, in easier way. You don't have to study them for a very long time. So AI could help here. Okay, but now we come to the last problem. This is the problem number 4, and this is the most fundamental problem, and I mean the most important part of my talk. Because when you think about general relativity and about mathematics in general, there is another growing problem. we become more and more sophisticated in the theorems that we prove. So they become usually longer and longer. So this is the story, of nonlinear stability of Minkowski spacetime. Probably you have heard about John Wheeler. He was a famous relativist. He coined the term black hole. So he's like a father of black holes, I would call him. And he had many famous students, including Richard Feynman and others. But one of his students, PhD student, was Christodoulou. And Christodoulou, he got as a topic of his PhD to prove nonlinear stability of Minkowski spacetime. And he did it, but instead of not in 1968, but in 1993. So you see, it was like 25 years later. And of course, he was smart enough to change his PhD topic to different topic, and he got a PhD earlier, but he started his talk. I was attending his talk in 2000 something, from saying that if he would listen to his PhD advisor, he would got this PhD after 25 years of studies. But he was thinking and working on this problem for 25 years. The proof has only more than 500 pages of very advanced mathematics. But you may see a clearer problem here. Yes, it was published as a book, and now you have to verify if this is correct or not. Let's say 25 years of work of the brilliant mathematician, and how you can do that. Okay, you can devote to this. It's easier to read it with understanding than to prove things, but you will need 1 year to do that, maybe 2 years. Okay, and nobody in academia can afford that, because you will lose your job if you will be reading one paper, one book for 2 years. So and you do not gain anything. You because if you find a mistake, okay, then there is no proof, but it's not it's an important achievement, but it will not support your career so much. So there are problems like that. And to put things to the extreme, the largest proof I have found, it had 10,000 pages. And in this case, it was written by 100 authors. Right? They did not write one book, 100 people, but the final classification of finite simple groups is based on 100 or more than 100 papers. It took a lot of time to write that. And the complete proof has 10,000 pages. So it's much harder to read that and to see if all this paper together are really give full classification of finite simple groups. Because if there is a mistake in one of those papers, then maybe this is not a full result yet, and we have to study that. Okay, so you clearly see that there are this kind of problem. Moreover, in the context of Einstein equations, because the idea that energy curve spacetime is the idea of metric gravity. How energy curve spacetime? To say that, you need to add equations. You can add Einstein equations, and there are the equations that are the most they are complicated, but the simplest among all equations that you can add to the metric theory. And they are tested by observations, so that's fine. But people are still testing different sets of equations, like modified Einstein equations. But again, if you will take modified Einstein equations, then this result doesn't hold, because it was made for Einstein equations. So you need to repeat this work again, 25 years maybe, and you can modify Einstein equations in infinite number of ways. So there is like a huge problem here, how to carry this kind of enormous research. And because the lifetime of a human being is finite simply, so you cannot spend too much time on one problem if you do not know if you will succeed or okay. So how to solve that problem and how AI could help us in solving that. This is the idea of formalizing mathematics. So imagine that you have something like it looks like a programming language, But instead of writing a code to do something with your computer, you turn mathematical proofs into a sequence of commands. And now, if you will use computer, it can check if it's logically consistent. Okay, it's because different people use different notation and mean different things, but sometimes by different symbols. Yes, so it's not easy if you will give this proof to AI in the full form, let's say this nonlinear stability of Minkowski spacetime. It's not easy for AI to analyze the logical consistency of that. But if you will formalize this mathematical proof and write it as a form of the code, then AI is much better at checking that. And checking that is just automatic because the results are 0 or 1. Yes, AI could help you to write a part of the proof in this formal mathematics language. But it can also, and you have already plugins for ChatGPT, for example, in Dojo, when AI could help you in proving new theorems. So if you will have a huge database of mathematical proofs, and you will train AI on this base, then when you will write new theorem, AI could help you to solve the problem, and it's already doing that. And you can check there is a free framework called Lean. It could be added to Copilot, to ChatGPT, and probably to other AI systems. The people behind the Lean and the people who promote, I would say, Lean and formalization of mathematics are famous mathematicians like Terence Tao. He's a Fields medalist. He was working in pure mathematics, but in PhD, in partial differential equations as well, that in things are relevant to general relativity. And of course, if you will have this system, you need more and more power to teach more advanced system, like the idea of Elon Musk, 100 of thousands, NVIDIA 100 units, and the Grok 3. And if you look at XI page, they have written the aim that they have. So the goal of the project is to understand the universe. So it's like our goal, I mean, scientists, cosmologists, astronomers, and so on. And if you know that Elon Musk's favorite book was Hitchhiker Guide to the Galaxy, then you of course know that the Grok 3 that will probably run next year, maybe, nobody knows exactly, is something that was called Deep Thought, the final computer that gives you answer about the universe and everything. You know the answer probably. And this modern formalization of mathematics now done with these systems with the help of AI. It's not new in the sense of the Hilbert program that started in the more than 100 years ago. And the Hilbert program was the idea that the whole mathematics could be derived from basic assumption. So you start with the axiom of logic, and then you derive from logic all remaining fields of mathematics. So it's like a tree growing. This program was killed by Gödel theorems. The Gödel theorems tell us that they could exist mathematical theorems that are always true, but you cannot derive them from axioms. There are like two versions of the theorem, but this is relevant for us. So if you will start a super smart computer, you cannot, starting with axioms, derive all the theorems. Now, so if you want to verify some theorem that you are convinced that it's true because you have tested like 1 million cases, then you need to go outside of the formal system. And there is a long discussion if this is a property of our brain that we are able to go outside of the formal system to prove theorems, because we can do that. I mean, mathematicians can do that, that are not cannot be derived from the basic axioms. So some people that say that only humans can do that, other people like Roger Penrose is saying that, other people believe that AI system like this one can work as a mathematician. And now there is a question. I already talking for 45 minutes, so I will end with this point. And now there is a question where we are now. And when you think about problems from International Mathematical Olympiad, then AI already scored at the level of silver medalist. So it's quite good, probably better than majority of us can do. But in recent weeks, Fields medalists, including Terence Tao and others, they constructed like something like ultimate benchmark for AI systems. They call it frontier math. So there are problems that are invented. It's not something for young people to do during the Olympiad. There are problems invented and created by the Fields medalist. And those problems can be solved probably by, let's say, 10 people on Earth, maybe not more. So majority of us, I mean, we cannot do that. And the idea was they invented new problems. The idea was that those problems shouldn't be in the training base of these AI systems. Because if you will have the same problem in the training base, then it's nothing strange that the AI system will find a solution. But they do not want to contaminate this training base. So there are like special problems that were not in the training base. And so far, AI system solve only 2% of problems. This is probably much more than any of us can do, but still Fields medalists are better at solving math problems. Now the predictions of Terence Tao are that in 4 years, those systems will solve like 80% of problems. He says that probably with the help of a graduate student. So you will have like, you will be graduate students, and with the help of this AI system, you will be able to solve mathematical problems at the level of the Fields medalist. And now, if there is some kind of barrier or not, we don't know at all. So maybe, I mean, so the relevant question is what will happen if all this AI system will become better than the Fields medalist, and they will solve a problem that we cannot understand even. And this is, of course, relevant for Einstein equations, and Einstein's equations are relevant for nature. So maybe this idea of Xi that will know the ultimate, that will know how the universe works using this kind of machine, maybe there is something in it. I don't know at the moment. So thank you for your attention. I think I will end here the answers.
So thank you very much for this interesting talk, and for also familiarizing all of us with the history and of those discoveries, and with those other more current context. And if anyone would like to ask questions, please write them in chat, and I will then read the questions to our professor, to our guest today. And I actually have a question from myself, because when you show those problems that had that were like the same solutions published in different years in different papers, I wonder how long it took until people realized that they were the same solutions, because it seemed that there were papers from the 20s and from the 60s, and you say that those solutions were written in different ways. So it must have been a lot of comprehensive work to come to this conclusion?
So it depends on the particular problem or particular solution I was talking about. But usually it looked in this way that after all this paper, somebody write another paper when he says that the paper from 1921 is the same solution as published in 70s. So it depends on the particular thing. And some things are, some people realize that some solutions given by one person are the same solutions are given by another person 20 years later, and they write the paper about that. But there come another person who look only at some another, let's say at this later paper, and still rederive some results of this older from the older paper. So it's a kind of a mixed and I would say, I mean, mess is the best word for that, maybe in English. So it's complicated. And even if you are, I mean, it's not so easy in general relativity to prove, even if you will come and tell me, I think those solutions are the same. Okay. So it's not so easy to find a proof that this is really a fact. So you need to make some effort to do that. It's not just, okay, I look and really they are the same. No, you need to do some effort. You need to do research to find that. There is a question in chat. I don't know if I answered your question. Gabriela, you are muted.
Yes, so thank you for answering my question. And there is the question in the chat. Is the use of AI at solving problems, in our example, Einstein's equation, actually a bigger problem discussed in science in general, or was it just an insight of what's discussed in astrophysicist community?
Okay, so let me read this question again. It's quite long. I have to understand it. Solving problems. I mean, so far, I mean, what I was talking about, it was mostly the future. So far, I don't know about any result that was discovered by AI. Okay, so I mean, it's helpful at some basic level, like you compare to papers. So probably many people do that. And as we know from other studies, many people use like ChatGPT to help them to write articles. You can discover that doing some kind of a statistical studies of the words that are in the paper. So so far, I mean, there are interesting papers in Nature, I would say, that people use AI system to rediscover physical laws, the laws that we already know. So I read a paper from Nature about rediscovering Kepler law by some AI system that was just looking at the model of planets. Okay, so we have a model of the solar system, and AI was it was not trained on this knowledge, if we believe the authors of this research, but it just rediscovered the law. So in some sense, I think it's possible for AI to find something really, really new, but in my field, it did not happen yet.
So there is another question. What motivated you to study gravity?
What motivated me to study gravity? I mean, because the gravity, in my opinion, and in the opinion of other people, is the most beautiful physical theory. Because there's a simple idea behind it, there is a complicated mathematics, and there are the spectacular results. And what it makes it interesting, especially for me, is, I mean, when you look at physics, what physics tell us about the world, that the world is not what we are thinking the world is. So the physical laws are very strange. For me, it's like a kind of magic. And the general relativity is full of this magic, because time is not what our brain thinks that the time is. You have this magical object like black holes when the time swaps in with space, and So for me, it was interesting because I wanted to understand that, if I can comprehend this in some way. And another interesting thing in physics for me is the quantum mechanics, because this word is the same crazy or even more crazy than general relativity. And of course, I was thinking about other more technical studies at the beginning, but then I read some books, and this usually starts with the books. I read Cosmology by Michael Heller. It's like when I was a young child, like 10 years old. So this is correlated to the books I have read when I was young child and I was in my high school.
And there is another question. What are the applications of studying gravity in engineering? And thank you for your presentation. I like it. It's in the chat.
Thank you that you like it. So far, general relativity, so Newtonian gravity is sufficient for majority of engineering application on Earth. But there are exceptions. One exception is GPS system. If you need precise localization, then you need to include the effects that the times flow at different speed, I would say this way, where the satellites are, than on the surface of Earth. So this time dilation, gravitational time dilation effect is there, and the time dilation from the difference of velocities is there as well. And if you wouldn't use that, then use general relativity and special relativity in this case, then the GPS would be not so precise. Another thing that is close to application of Earth, when you want to study the gravitational field of Earth, or even geological form of the Earth, because you can nowadays you can measure time with so high precision that you can tell, for example, that the time is passing at different speed at the top of my nose and here. We have so precise instruments. And now if the time flow speed of time depends how far from the center of Earth is, or from the what is the mass distribution in Earth, then you can make maps with that. This is still not at the commercial level, but there is Eva Hackmann in Germany, I think, and she's relativist working on this kind of application. So far, they need like a huge car to measure this with this precision, but in future, I can imagine that this will be at the commercial level. And those are those practical applications. And of course, if you think about like future, not what we have at the present time, space travel, then this relativistic effect could be important. At the moment, I think you don't need much corrections. If you will go to Mars, I think the relativity won't be so important, I think. That there will be like a Shapiro time delay when you send a signal, but for the trajectory, I'm not sure, but I think there are no such huge effects. But in the future, of course, it will be important.
Regarding the time delay, I think when somebody has an opportunity to look for like rover competitions, like for European Rover Challenge, for example, which was a competition of student-made rovers, they decided to simulate that signal delay, so that people standing and looking at their model rovers had to wait for their action. And there is another question.
But you mean the delay between sending signal from Earth
Yes.
to Mars?
Yes, okay. this delay. And so another question. Thanks for such a nice presentation. I have a general question about gravity. That how do the gravitational forces of the Sun and Moon interact to create variations in Earth's gravity, and how are these changes related to tidal phenomena? We have seen some major variation recorded in ancient sediments.
So I mean, so these tidal things for Earth, there are not, there are like it's, I mean, it's sufficient at the level that we know them to calculate it using Newtonian gravity. So this is not related to general relativity. But of course, I mean, the explanation is that the two-body system like Earth and Moon is spinning around the center of mass, so it's not exactly the center of Earth, and so the gravity force from the Moon caused tidal forces on Earth, and you could see tides on Earth. In astrophysics, such effects are important. For example, when you have like a collision of black holes and neutron stars, you can study the equation of state of the neutron star, seeing from the profile of the gravitational radiation how it reacts to the tidal forces from the second body, like a black hole that is nearby during the collision. Okay, so I don't think I can say much more on this problem. And maybe I will add that I was talking to Eva Hackman during recent conference, and they said that, of course, when they study this gravitational field of Earth, using this relativistic approach, they have to include the Moon and so on because of the tidal forces.
Thank you for answering the question. As the person who asked the question isn't asking for clarification, I think that this answered this question comprehensively. And now another question on the chat. I have a more historical question. You said Einstein didn't believe that black holes can exist. What's the reason? I'm wondering because Einstein was opposed to quantum theory too, and now we know that both things are actually true to some extent.
So Einstein was wrong from time to time and even quite often. But so the question is, why? What was the reason why he did not believe in black holes? And the reason was like a very reasonable reason. When you will take a Newtonian theory, imagine that you make a ball of dust in Newtonian theory. So you have like all these particles, and then you switch the gravity. So this ball of dust will collapse to the center. Okay, and if the particles you model in this dust, what I mean by dust is something that doesn't have a pressure, then you will have finite number of particles at the center at small point, I mean at just single point. And this means that you will have in very small volume finite number of particles in infinitely small volume, and this means that the density in such system will blow up. But this is, I mean, we don't see this happen in nature, yes? Because what happened here, I tell you about this blow up of density in such system, it happens in our mathematical description of this. This is an example of singularity. And then if you will take the solutions to Einstein's equation that describe black hole, and the solution that Einstein was aware of, this is the Schwarzschild solution, it's spherically symmetric, exactly as the system of dust, and is singular. At r equal to 0, this is not exactly the center, but you look at that time as the center of the system. So Einstein was thinking like the people in 19th century. When they see this kind of singularity, they said, okay, your theory do not describe this well. So I don't believe that this object exists in nature, because the singularity blow up of something indicates that your model, mathematical model, failed. And when you take this Schwarzschild solution, you have exact blow up of curvature at the r equal to 0. So for Einstein, it looked like something that indicates that these things cannot exist in nature. And nowadays, we have evidence that he was wrong. We have evidence in terms of the gravitational waves coming from collisions of black holes, and we have even images of black holes with Event Horizon Telescope. You have seen several of them in recent years. So those things are, I mean, the gravitational waves are very consistent, I would say, with black holes. So we believe that this is true. And of course, we have the singularity at the center, and we don't know what is there because our theory fails to tell us what is there. So maybe if we learn how to construct quantum gravity, maybe we'll learn what is in the center of the black hole. At the moment, we don't know, but this is not the reason to throw away this solution. This we are quite sure now. And Einstein, he was in some sense right that using the knowledge he had that was built on this 19th century thinking, that he dismissed these solutions as not physical.
Thank you for answering the question. And we have another message on the chat. Thank you for this informative lecture. My question is a bit spooky, I guess pun intended. In your opinion, does universal inflation works on atomic scales, for example, may it disrupt quarks pairs?
So this question was asked in a movie by Woody Allen, Annie Hall, in the 70s, when there is a young Woody Allen, and he worried that universe expand and the universe expands, so everything will break away and there will be end of the world. So now, if you think about inflations, there could be, I mean, the cosmologists could mean two things. When you say inflation, so majority of people think not about just expansion of the universe, but about inflation at the early stage. At early stage, it was like expansion of the universe, but it was much faster, extremely fast and rapid event. And not everyone believes that this really is the true physical thing. It's needed to explain several things, but there is no agreement at the moment. Probably, but the universal inflation, you mean just the ordinary inflation, ordinary expansion of the universe. And now this expansion of the universe, it's something that happened on the cosmological scales. And this question was studied by Einstein and Strauss in 1945 or 6, I think. So they constructed a system within general relativity. The system was like a galaxy in the cosmological solution. And it follows from these studies, but this is not definitive answer, that such system doesn't expand. So when you think about, but this is what we observe. When you look at the scale of the galaxy doesn't expand because it is a gravitationally bound system. And in this case, we believe that there is no this global expansion. So the expansion happened not even between two galaxies. You need to go to scales like half of the gigaparsecs. Shorter scale, sorry, this is the scale of the homogeneity, but general, it's not even sufficient to go from one galaxy to another. Some galaxies are moving toward us because of the gravitational pull. So definitely there is no standard expansion at the level of elementary particles. So this is what I can tell you. I mean, the reason is that people could believe in that there is this kind of expansion is some kind of a misunderstanding, because the cosmological model is homogeneous and isotropic, but assuming this, let's say, 1 gigaparsec or half gigaparsec scale. On smaller scales, it's inhomogeneous, so the model doesn't tell you how the universe behaves there. You need extra models or extra description or extra perturbation to the cosmological model, and then there is no this standard expansion, no Hubble flow at this level.
I suppose that those additional perturbations would need even more computational power to predict what would happen on smaller scales if someone was interested. And there is another question. So time-space on short scales is static.
So this is a continuation of this question.
Yes.
Yes, I mean, to extremely good approximation is static. This is why we can use flat spacetime when we think about electrodynamics and such things. When you calculate things at CERN, we use just flat spacetime, not this cosmological solution. So for all the practical purposes, it's flat spacetime is good approximation here. To the local problems, yes, because when we study movement around the Earth, then it's a different scale already, astronomical scale, and you need to include curvature.
Thank you for answering this question as well. And
there's one more. I was already seen. Where is the threshold? The threshold is not definite. Nobody really knows, but definitely is beyond our galaxy. And it's not a sharp thing. Yes, it's like imagine that you have some kind of a soup, and it's homogeneous on 1 gigaparsec scale. And when you look at smaller distances, this expansion is not homogeneous. And when you look at the really small scale, then there is no expansion. So in our galaxy, there is no this kind of expansion.
So thank you for this explanation. And I think that there are no more questions for now, I suppose. So thank you again for this very interesting lecture, for taking your time to answer all of our questions, and for telling about all those interesting things today. Thank you so much.
Thank you for invitation, and thank you for coming, virtually coming to my lecture. Thank you for your attention.